All right, it's been a busy week for us. We had a lot of things to fix. We've had a lot of discrepancies between our developer and prod and everything, and but I think we've gotten it all kind of tamped down. If you guys have any issues with what we've covered so far, please post that stuff, and our team will be working on fixing it. But we'll be moving into a new concept today. But we're going to just be focusing on this one concept because it's pretty complicated. And then we're going to put all of it together into kind of our first coherent, intelligent agent. So, in previous conversations, we had talked about, we set up our bot, we got some input, echoed it back, got some output, and then we added the text generation so that we could actually generate something and respond. And then, we wanted to add some state, like, hey, I want this thing to sort of respond not just to what I just said, but maybe to what I said, three turns ago, 3 sentences ago or whatever. And so we added short-term memory with events. Now we want to add long-term memory. Our agent, it has a very short buffer of our immediate conversation, saying, hey, what's up? Not much. How you doing? And as it gets longer, we start to lose the personality of the agent. So if you guys have been working with short-term memory at all in your own agents, you've probably experienced this, where as your conversation gets too long, you have to, well, trim the conversation down, probably make sure it's only the last X lines. And you also you probably lose some of the personality of your agent. And part of that is because, well, let's just go back to the sandbox really quick. In the OpenAI sandbox, let's just say I want to go to the playground. Whatever I type up here is going to be weighted less than whatever I type down here. So there's been a lot of research on this, especially when we're doing multi-shots, right? Like let's say I'm saying choose an appropriate task for the sentence I want to browse the internet. This is a kind of common thing we do. And then we might say, I don't know, browse, right? Now I might say have another choose an appropriate task for the sentence I want to get the time clock. And the order of these actually matters quite a lot. So there's been a lot of research into how part of the fine tuning of your prompt could even just be changing the order of your examples. And I could demonstrate that. So like I say, choose an example, appropriate task for the sentence. I want to order pizza. And that might be, I don't know, Uber Eats. I don't know, whatever. I don't know. Let's see what it gives us. I press submit. And it gives us order. Cool. Okay, order makes sense. It might just do that no matter what. But sometimes if I were to change these around, for example, I might get something different. So this especially becomes a problem when you have conversation and it starts to kind of get rid of whatever is at the top. I didn't make a very good. I want to juggle pizza. How about that? Juggle some pizza on my nose. And depending on, well, I guess it's actually just learned. It's pretty smart. Maybe I have to use a different model. But depending on the order of these, it'll oftentimes change what it thinks the task is and how it executes the task. And even worse, I might say like, you are an agent, blah, blah, blah. And then as my conversation, maybe my conversation's down here, right, gets really long, blah, 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 user, blah, you start to lose the weight of the context above. This is a common problem and something that some of our own alpha users have mentioned is like, hey, how do I solve this problem? And my context window is getting too large for the conversation, but I still want to remember things that happened earlier in the day. So we need this kind of long-term memory function that solves these two things. One, we can find relevant context about our agent and bring it in whenever we need it. Instead of having some super long bio and long conversation, long descriptions, long conversation, and finally get to what we're actually trying to respond with. We could say like, oh, they're asking us about, our eye color or something. Well, let's go and find any information we have about our own eye color in our like list of bio database or whatever. And let's also go find information if we've ever talked to them about eye color in our conversation. And so that's the thing we're going to really focus on today is simulating long-term memory in agents using vector databases. So there's a lot of terminology, and we're going to kind of start really at the beginning of that. I hope this kind of makes sense. If you haven't run into this problem yet, you probably will. Basically, whatever starts is at the bottom is more relevant to whatever's going to get predicted than whatever's at the top. And there's been some research into these transformer models that this is a very common, prevalent kind of thing. And we don't have a solution other than to sit there and reorder things until we get it the way we want. The way we do it in Magick. And one of the really powerful things about Magick is that we can dynamically create this prompt, right? So we can inject things as needed. Instead of having super long prompts, we can actually have very short, specific prompts. But to get there, we need this other thing. So that other thing is called embeddings. Embeddings are, well, we're going to cover what exactly they are. And we're going to start from the very, very simple version of this and then get into the more conceptual. But embeddings are a byproduct of machine learning models. They're something that a machine learning model can create. Some models only create them, and other language models, specifically, or image models, can create them as sort of a byproduct of a larger process. And that's what we're doing. So first, we got to start with what is a word? We know what a word is. Let's say I think queen and king are good. That's kind of in this example. What is a queen? Well, you think of all the stuff of what a queen is in your head, right? So a queen is just a word, and it has we can assign that some token if we go to as we've done with the tokenization in the previous lessons. Maybe we'll even go to the tokenizer and look at what that is. Let's just type in queen, right? And I show, and you can see it's two words. What if I actually do it with a Q, with a capital Q? You can see it's one word, right? So queen, capital Q, is a single token. It's got some ID. The ID is 32466 of that token. And in addition to that, it has all kinds of super complex relationships to every other word. When I say queen, you might think, oh, chessboard. You might think Queen of England. You might think Freddie Mercury, right? And it has deep relations to all of those different things. Queen is not just a simple thing. So the way it learns those relationships is that we make a model. Usually we just look at what words it's close to. And the closer it is to another word, the Queen of England, for example, the more likely it is that Queen of England is the relationships we're looking for. We also tend to filter out simple words, articles like of, the, because they are related to everything when we're doing these kinds of vectorizations. It depends. Sometimes we do, sometimes we don't. Sometimes we also capitalize everything or lowercase all of it, or respect the case. So queen capital Q is different than lowercase. But and you could think well, if you see queen capital Q, that's probably talking about the band, as opposed to the queen. And those are different words with different relationships, in different sentences and contexts. So we have the very simplest way that we record what the relationships of a word is we transform it into a number, and we describe that number in space, in 3D space. And so let's throw away the number. Let's just think about this as the word queen, right? Obviously, queen, we could say, well, it's definitely closer to king than it is to banana, right? Banana is probably let's just say you're just kind of measuring the distance of words to each other, right? Okay, queen is close to king. It's very far away from banana. It's pretty close to Freddie Mercury. Freddie Mercury is not that close to king. So there's got to be some sort of 3D relationship where we could ideally put all of the words where they're closer to other words that are similar, and they're farther away from words that are farther away in conceptual space, or even just in how likely they are to be near those other words in a sentence is the most basic version of this, right? And typically, queen and king are very similar, right? They clearly have a relationship between each other. And you might say the king and queen of England. So they're very often represented near each other. And also that we tend to see things in these kind of opposing sort of dualistic ways where the duality of something tends to be very close to it. And I as a brief aside, if you've ever heard of the Waluigi effect, you should really Google that and check it out. It's really interesting. But it's this idea that anytime you try and pull something out of a language model, you also can get the opposite of it, because so much of our language is about defining opposites. So we have the semantic relationship between woman and man, king and queen, big and biggest, or small and smallest. These are all quite, you can kind of easily imagine them. Now imagine each word has is a point in 3D space. Like you have a little spaceship and you could fly around the universe and you could fly to each of the different words that exist. And they might be clustered together. You know, king, queen, pawn, bishop. That's all like over in a cluster. And then you can see there's this weird other, like what's called orthogonality, which is totally other, dimensions of cluster of queen, great white, America. Trying to think of other 80s bands, Pink Floyd or something. I don't know. Not really an 80s band, but they're still alive. So there's this like relationship of bands to Queen. Then there's like the Queen of England, the Queen of Denmark, whatever. There's these all kinds of different complex spatial relationships. So obviously we can't really get all those words to fit together in this way in 3D space, but it's nice to kind of visualize it this way. So this is, I'll show you the dimensionality in a second, but let's just imagine that we're clustering the words in the Bible by 2D space. And you can see there's like James, Jesus, Peter, that's all kind of over here. Then you have like God, Christ, gospel, that's over here. You've got like famine and pestilence over here. And so you have these kind of clusters of concepts, right? And obviously there's some relationship between Jesus and Christ. Like there's quite a lot. But imagine there's like a wormhole, like another hidden dimension that connects these two concepts, right? Beyond two-dimensional space. And so the more dimensions of our vector, the more of these complex relationships we can define. Sorry. And cool. And I'll show you a complex dimensional vector in a second. But just imagine for your own brain sanity, this 3D is a really good representation that you're really looking in concept space for between these kinds of things. So let's talk about like what is a concept. Well, first, one other thing to point out. We're talking about this in the concept of words, but you can kind of embed anything that goes into a machine learning model. This could be audio, it could be images, text, video, obviously, like whatever you can get to be seen by the model's going to take that and it's going to convert it into some numbers. So when you actually look at like an embedding vector of like I have this image here, you can see one of the problems with the image is if I were to like record the image, well, then maybe other people could see the image. This is this fear that artists have that like the image is in the model somewhere, blah, blah, blah. Like, it's not really how it works. What we do is we convert it to a series of numbers. And you can see that parts of the numbers are going to reflect different concepts in the actual image. We get that embedding vector, and now we can work with that. And this is how we do things like stable diffusion. We have an embedding vector for an image. We have an embedding vector for some word description. And we can actually, now they're the same. They're the same dimensions. They kind of point to the same concepts underneath. We've linked these images and words together through this sort of intermediate numerical representation, which we call an embedding. So the last thing is like, what is a concept? We talk about concepts a lot. Well, I mean, it's the concept of queen, right? You know what a queen is. You know what heraldry is. You know what the crown is. All these other. You have all these other images, and sometimes like you could describe a concept with completely different words than I do, but there's still a deep link between those concepts, especially in a massive language model that can like do those leaps, like the GPT models can. Right? They can actually look and say, well, that's conceptually very similar. You're talking about, the royal crown over here, and you're talking about the Queen of England over here. Like those are clearly very similar ideas with totally different words. And so this abstracting away specific words and specific images to a deeper conceptual level lets us do just like absolutely crazy stuff. And it also, I think, points to how our brain kind of works. When you think, when you're dreaming, you have like, it feels so important because even though the actual end result of what your brain is experiencing is very abstract, there's clearly strong conceptual bases and like concepts there that your brain is processing and working with. And this is probably very similar to how, why our models are working so well, is a bit of that kind of neuromimicry. So we've talked about embeddings. Now, if you're not a math person, vector might sound kind of scary to you. What is a vector? Well, it's a way of recording. We use vectors for all kinds of things, but the simplest conceptual way is that you have kind of an XYZ coordinate. It's a little bit over to the left, a little bit up, and then maybe a little bit forward. And you can describe kind of everything in that space. That's called Euclidean space. That there's sort of 3 dimensions. Or you could even say it's 2 dimensions, right? We have an X and a Y. And so everything in here is represented by some sort of position. If it was 0, 0 down here, then like this is like, I don't know, 1, 2 or something like that, right? And each of these positions could be recorded just kind of by its coordinate. Afflictions, right? All I need to know is its coordinates. And then I need to know the coordinates of Moses over here. And then I can measure the difference between them. I can actually calculate the length of the space between them. And I can judge how similar they are by how close they are in 3D space. And the actual measure of a thing in what we call n-dimensional space, which could be 2D, 3D, 15,000D, is that number that we get is a vector. A vector, an embedding, is displayed to us as users as a vector, right? It is a collection of numbers. And a vector looks like this: 0, 1, 2, right? You have the bracket indicates, hey, this is a vector. You have a 0, you have a 1, and a 2. So that's like X, Y, Z, right? That might be a position in space. The other thing we use vectors for is direction. So it could be X, Y, Z position, but it could also be like which direction is that vector facing. And so now you have 0, 1, 2, but you might also have like 2, 3, 4, like for position and direction. Now you have this whole now you've got 6 dimensions of vector. Now imagine it's got time. Now imagine it's got a color property and it's got a mood, and now you're in like 20 dimensions. So you can kind of just assign each of these numbers to be a dimension, which could be X, could be like my happiness value. We don't assign them in language models. We train them, and then they become these very abstract things that are hard for us to read or grasp. When people say machine learning is a black box, that's because we don't know what the labels are for the vectors, more or less. That's like the heart of it, right? Like it's basically a massive vector processing machine, and the vectors are unlabeled. They're just random numbers, and then those are these kind of random weights, and then you calculate something and you get this thing back. And the reason it's a black box is because we are not telling it what those values are. It's not X, Y, Z in 3D space. It's some crazy conceptual space that none of us understand. And if you take 2 models and you have like 2 different models and you have them train, they'll come back with completely different vectors for what each thing represents, because they're all relationships between each other. So vectors, all of this comes out of linear algebra. Linear algebra is usually a course you would take either before or after calculus in college if you're interested in engineering. There is a great, one of my favorite teachers ever, Gilbert Strang from MIT. He's been very adamant about making sure that all of his work is online for free. So you can get MIT linear algebra here from Gilbert Strang, who literally wrote the book that we all read on linear algebra, and it's all on YouTube for free. The entire course, all the courseware, everything. And this is how I learned. And he's very influential, I think, on how I would love to teach. I don't know. He's just very, very thoughtful person who takes you on a journey. I highly recommend these videos if you're interested in this space. The other really helpful one is 3 Blue, 1 Brown, who kind of does a lot of like visual explanations of vectors. So if you're really struggling with, some of the conceptual stuff, I highly recommend this video as well. Explains coordinate systems. You can kind of see different vectors being measured out. And yeah, we're working in these like high dimensional, crazy deep learning stuff, but really it's just like a massive repeat of this very simple concept. So you don't have to know any of this stuff, just so you know. This is nothing to do with anything of like actually getting an output, but I think it really helps me to conceptualize what's actually going on. Like when I do a similarity search, what is similarity? It's like, well, these things are close together. They're like each other. Okay, cool. I added a little math visualization thing here. But yeah, pretty much what you should know is that because the vectors are these sets of dimensions that are uninterpretable by humans, we pretty much just move them around. We don't change them. We can't read them. No scientist can look at a vector and be like, oh, well, clearly that's, there's none of that. That's not how it works. It's totally black box for us. And that's very convenient, actually, as most of us are probably not super hardcore math people. You can see here, I've got some vectors. That, beyond this kind of basic conceptual understanding, don't worry, you don't have to know too much. But I did want to introduce you to it and let you kind of know, like, this is what's happening underneath. Linear algebra is probably the most important math for game engine development as well as for machine learning. Obviously, calculus is helpful, but it's really a lot of this. Now, I'm just going to make a vector for you guys really quickly. I have one vector. And I'm going to just say, like, well, my 0, 0, 1 vector just points straight up, right? And maybe my 1, 1 vector, well, you can see it points straight up and to the left, because that's x1, nothing, and then y1. And this is basically an extension of what you might have learned in, like, Algebra 1, y equals mx plus b. Kind of like that, except that we now are working in 3D space. Great. You kind of get... Hopefully this kind of helps you guys grok it. I highly recommend you look at this on your own. Good deal. Okay, we did it. We got through vectors. So what can we use vectors for? Well, let's talk about what we use embeddings for. Obviously, embeddings are a type of vector. Cool. We can turn a word into a vector using a thing called word2vec. We can turn a image into a vector called image2vec. It's a machine learning algorithm. We can also turn an entire sentence into a vector using setFit, which is a sentence transformer. Or we could maybe do a more high dimensional thing and use, like, OpenAI's models to create, like, a really high dimensional vector of a paragraph. So I'm jumping around a little bit here, but I'll show you. This is what an OpenAI vector looks like. This is for the word, this is a test. I typed in, this is a test of the sentence. I used the Ada embeddings model from OpenAI, and it gave me back this thing. It keeps going. It's a lot of numbers. It's 1536, right? 1,536 dimensions. Each one of those represents some sort of abstract thing. It could be happiness. It could be like royalty-ness, like they're all sort of conceptual weights towards things that matter, and some of them are even interdependent. Could be like there's like an animalish one, but then there's kind of like a furryish, I don't know. You could have like all, like, what these actually represent is not one thing, but sort of a relationship of concepts to another thing. And so each of these dimensions is like where it is in that space. So if we were to simplify it, let's just say the first number was like the happiness space, and a negative number would be unhappy, and a positive number would be happy. Then you'd say, like, well, this is a slightly unhappy-ish number. Cool. I don't know if that makes sense, but you'd see it's it's kind of negative 0, 1. It's like more unhappy than it is happy, and maybe this one is the coolness vector, and a negative number is less cool, and but realistically, they're much more abstract and complex than that. However, when we were first starting and making machine learning models, and you do something like classification, that might actually be how you do it. So, let's see. Let's jump back up for a second. So we got through all this. Kind of talked about how we get a word or sentence to a bunch of vectors. We use a language model in our case, or we could use a dedicated model that creates that intermediate step as an output. Here's an example, a 2D example of concept embeddings of different books. So you can see, the Encyclopedia Britannica is over here in this kind of blue area, which is kind of the sciencey area. It's in the green area, the nonfiction area. Then we have the Encyclopedia Fantasy Fiction or whatever is over here. We have 1984 is kind of in the middle as a novel. These kind of novels. Then we have like Dracula's over here. It's sort of more of a horror thing, whatever. There's sci-fi fantasies over here, non-fiction's over here. Everything else is kind of in the middle somewhere. And you can sort of figure out the relationships between the labels. Like, what are they're labeled, probably what they are, when they came out, what genre they are. And those would be like relationships that they have between the different sort of, how close two books are together. And you can imagine some places where you'd use this, like a recommendation engine. Oh, you like Don Quixote? You might also like Jane Eyre. They're very similar books that came out and blah blah blah. Another thing you could do is measure like, oh, you and these 10 other people like this plus they like that, so let's make a relationship between those, and then we can create an embedding space out of that. We can do like some other users like this, so you must like it as well. Another thing would be like sentiment classification. Like, well, we have a bunch of like really ugly tweets up here and a bunch of really nice tweets down here, and wherever your tweet lies is like, is it ugly or nice? Um, so, long story short, this is all happening under the hood. You don't really have to know how any of this stuff deeply works. It really just helps to have a little bit of intuition. But the computer's going to lift almost all of this for you, and we've built quite a bit of stuff into to also abstract this. So I added a little bit of further reading. There's a whole Google developers explanation on this. They have a video. It's 15 minutes. They give you some different trainings, but this is probably pretty hard mode for most people here who aren't ML researchers. So I think I included a more just straightforward like word embeddings explained video here. And we'll give those in the lecture notes. Also, some people are posting some really great posts to the chat as well, so maybe we'll include those as well. Okay, so you've got your embedding, right? Somehow magically you've used our node or whatever, and you've got your embedding. Well, now you want to go and find similar things to that one. So you typed in chair, and you want to come back with like, I don't know, or let's say I don't know, let's give it a better one. You typed in like guitar, and you want to come back with a similar list of objects, and it comes back with like drum set and bass and banana and towel. You're like, okay, well, clearly some of those are more like this than the other ones. So, how do I measure that? There's two ways. One way is we basically go through the list and we just compare it. Like, is it closer to this one than the last one? Yeah, it's definitely closer to bass guitar than it is towel, so probably more that one. And it kind of just like goes down, our spreadsheet and compares each one. And this can be very slow. I have to compare every single thing to every other thing, basically, to, or in this case, just compare like my input to all these different saved things and find the closest one. And I have to calculate that every time. And so that's like the slowest way that it's been done. After that, people said, okay, well, there's probably a better way. We can do like a tree. And with that tree, we came up with this thing called K nearest neighbors. K is a representation of like a, in math of just like one of the options in a set, right? We have a large set. We want to, which is just like a list of whatever our concepts. Of those concepts, we want to find the nearest neighbor. There's a few different nearest neighbor being like the most similar concept. So K and N is like slightly better than just like brute force checking against every one. It is using it's creating a tree and then measuring how close our thing is to each of those in the tree in a way that's computationally better, but not ideal, right? So we use a traditional database called Postgres. Sorry, this is a bit nerdy, but if you're, to get into the weeds a bit, we use Postgres. It's a very popular database. And internally that has KNN search through what's called PG vector is the extension. But it's fine. But you've probably, if you've looked and you've been following the space at all, you might have heard of like Weaviate or Pinecone or Haystack. And these are popular vector search databases. And they use a different kind of algorithm, not KNN, not just like go through this tree and find the nearest neighbor, but they actually, they don't care about the exact nearest neighbor. They care about the approximate nearest neighbor, and they want to do it as fast as they possibly can on millions and millions of different concepts. So if you stored, 50,000 different conversation snippets that you had, you just want to find the one where your eyes are blue, what you really care about most is like how fast you can get that response. A good quality response is important, but also you don't want it to take like 10 seconds every time, you're searching for that thing. It would just make the whole thing really, really slow. So, so there is a better algorithm called approximate nearest neighbor, ANN, or it's a class of algorithms. And within that, there is a specific algorithm, and all vector search databases use this algorithm. I've included the paper. You don't have to read it. It's super dense, but it's really interesting. The basically the insight is, let's make a little world and let's navigate it and let's create a graph with the jumps from each place to each other place. And so this is basically the pinnacle of graph theory and thus search and all that stuff. This is like the best thing. So someone made a library for this, and then everybody else said, great library. Let's go package that and make it into a product. And so Weaviate, Quadrant, or Quadrant, whatever they're called, Chroma, Pinecone, Haystack, Milvus, and Feis, they all use HNSW. Under the hood, they use the same libraries, slightly different implementations, but they all use this hierarchical, navigable, small world ANN thing. Now, very complex and conceptual. Basically, the difference between all of these things is like, what language was it implemented? How well was it engineered? How fast is their cloud? What are they charging you? Like, it's much more mundane stuff than like, but like at the bottom of it, they all basically use the same algorithm. So the main takeaway here, if you take away anything, is there are many ways to store and retrieve this data, but there's kind of one best way. So pretty much all the options do it the same way. And the differences between them in terms of speed and cost and scale and stuff are basically how they were implemented and engineered. And I can't recommend one over another. They all have different things that are good about them. But some of them are free and open source, and some of them aren't. We like Weaviate because it's free and open source. We like Quadrant because it's got a great Python integration and it works really well. In that kind, it's very fast. We like Chroma because they're friends of ours. They've helped, like, they've solved some of the pain points of Weaviate, basically, specifically. Pinecone's fine. They're really good at marketing, but they're a closed source thing, and you have to pay them a lot of money, so I don't use them. Haystack, same. Milvus, I've heard good things about. I don't know. And Feis. Feis is Facebook's version of this. It's free and open source, and it's kind of like a lot of the research side is going into there. Cool. I think we got through most of that's probably going to go out the window. It's a lot, yeah. Someone's saying magic number. This is like some serious magic numbers kind of business, right? FYI, where we're going is currently we support the KNN thing, yeah. We did support Weaviate, but we found that it was a really bad user experience, and there was just like a lot of issues that were going to fall downstream onto our users. So we've actually started integrating LangChain.js. LangChain is another software that kind of does a lot of what we do, but it's really geared toward coders. So under the hood, we're sort of moving that way and building LangChain into what we're doing, and that will mean that it kind of opens up all of the different options, and so that's something in the future, coming to Magick soon, will be an integration basically with all of these libraries together, whichever one you want, as well as the KNN Postgres thing, just to get you going quickly. It's very lightweight, and we'll be basically supporting all of it. Cool. So, what can we use this for? We kind of went over some of these tasks, but really, there's, I'd say, 3 tasks we use them most for here in our system, and really one that's the most important. Classification, right? I have 10 things this could, let's say I have, I'm trying to determine the emotion of something that's coming in, just down to like one word. Is it angry, happy, sad? And so I might have descriptions, like vector embeddings, of different happy things and sad things and angry things. And I could compare, like do a search and say, well, this incoming message, this incoming tweet, is most like this other really sad tweet that I've labeled as the most sad. So clearly it's it's a sad tweet. And the result of my classification would be sad. And among classifiers, this is not the most efficient way to do classification, but I can classify infinite topics. It can classify as, like, if I have 1,000 emotions, I could have each emotion be assigned to basically a vector, and I can do that all day. And one of the limitations of a lot of classifiers is they tend to have a very limited number of labels I could apply. So search could be used as a classification tool, especially for like larger open-ended classification. Retrieval. This is the biggest one, right? This is going to be our big deal. I want to go get something that's similar to what I'm looking for. And this is how we'll do long-term memories. Like retrieval is the word, like the technical word for what we're doing, and the technical loop that we're doing is retrieval augmentation for language models. There's a great paper that came out. So we're doing external retrieval. There's a great paper. Let's see, retrieval called Realm. I think there's another one called ROM, but I couldn't find it. But they're basically doing this kind of retrieval augmentation while they're training the model. Very cool, very integrated. We're doing what's an external retrieval. So we retrieve the context from our vector database, then we feed it into the language model. It's not like one system. It's two systems that talk to each other. But that's nice because it's very flexible, especially when we're prototyping, to not have these things be separate. Cool. So the last thing is moderation. We could have like a list of horrible things people have said to each other on forums, and then we could kind of compare anything that comes in and say, wow, that's really similar to that horrible thing somebody said. That probably isn't going to pass our standard. And so we can use this as a moderation tool in the future. But really, what we want to focus on is how we can use retrieval. Specifically, we want to simulate long-term memory, right? I mean, that's the deal. Like, we've got short-term memory. Now we need this long-term memory. We can do that with retrieval, and we can use vector search to do retrieval, and the vector search is searching through embeddings, connecting it all together. So I think now we're ready to go into Magick. Does anybody have any questions, concerns? What the heck? Oh my God, that was so heavy. Anybody fall asleep yet? Okay, well, we're gonna get to the fun part. Okay, I've got Magick. So let's say, well, let's just start with our simple loop of short-term memory. We want to take in just like testing, and we just want to like store that and then make sure that it's actually coming back. We'll start there. What we did last week, we're just going to start with short-term memory, which are basically just events. Those events are stored in rows in a spreadsheet. Well, we call it a database, but it's just a glorified spreadsheet. And we can get the last 5 events or something like that. And that's a good, short-term memory approximation. So the first thing we'll do is we'll make a event recall to recall our last events, and we'll name that conversation. It could be anything, but we are doing a conversation, and we want this to be our short-term conversation memory. You could also have like actions, you could have tasks, you could have all kinds of stuff here, but we're doing conversation now. And let's say we'll wire that up. We have to execute the trigger so that it executes before our echo. And we should probably have an events to conversation node. What this node does is it takes the events and it formats them in kind of a script. So it's like, the assistant, the person, the assistant, the person, whatever. Just basically takes the last events and formats it for us. Cool. Conversation takes the input event because it's storing all of the data from the input event into our new event. And you can see there's an embedding input, and we're going to ignore that for now, but we're going to get to that in a second. That's clearly very important to what we're doing here. And now this we will just wire up. I would expect the first time for it to be null because we don't have any events. We'll get to that in a second. So we call the event, we convert it to a conversation, we echo it. It's probably empty the first time, right? Because we haven't said anything yet. We output it, and then we store the event. And I will go and I will say, let's see, events, event, store event. Now I actually need, for this we'll just do one event. Now if I was doing a conversation, I'm going to store 2 events. I'm going to store the event for the original thing that came in. Yeah, maybe we'll just do it this way. And then, because I'm going to store the event that, came in, and then the event that went back out, the agent's response, right? The sender's input, the agent's response, those are each different events. Combination of the 2 events makes a conversation turn. The conversation gets loaded into this event. We load the last 6 events, which equates to 3 conversation turns, back and forth, back and forth, back and forth. We convert that to a conversation, and then we echo it, right? So the conversation should build up as we store events. For now, we'll just store this one event to keep it simple. Store event, and the data that I want to store is this content, and I want to make sure that it is getting the event information, and that's it. I don't have to override the sender. I'm going to use that for the response from my agent when I want to override a sender to be this one, not the input event sender. And obviously, we're going to get to the embeddings here in a second. Save the spell. And just refresh. Sometimes our WebSocket connection does not connect. You can see testing. So what happened? Well, it gave me a blank response. Did it store the event? Did not store the event. Well, it does seem to be working though. So team, if you can take a look at that, I am on the cloud. Should be storing the event. Let me try and refresh here. Testing. And well, we might not have dice on that right now. Yeah, it's not storing the event. Let me try Cloud Dev really quick. So I tested this earlier and it was working all right. While that's building, take a second. We can let's imagine that it's pulling in, which it should be. We also have a dev server, which I'm gonna try in a second. Although I might have to log in. Type that in over here on my second window, and I will need to sign in. So if I have this here and this is in Cloud Dev, that's great. Sometimes if you're in local development, you're like, wow, I really like this spell. I wish I had it somewhere else. I can export it. Just export spell. And then I have a Cloud Dev over here. Let's hope it works. And I can import spell. And my downloads folder wasn't too bad. Sometimes it takes a while. And there you go. I've imported that same spell into. Now I'm actually in a different environment, different copy of Magick here. Now, does it work? Maybe. Hey, it did something. Yeah, it did work. You can see it recalled a whole bunch of events, right? And if I go here, I can actually see there are a bunch of events already here. Solid. So hopefully the team is rushing to fix this on the cloud so that it works for all of you. If not, we do have the dev server. It's working, so we probably just need to push this from our to production for you guys. That should be working within the hour. Cool. So we're storing the event, but there is no embedding associated with that. It just comes in, and if I wanted to search for it, I can't. It has a null vector. Basically what it means is that there is a vector there, but it's like it has no opinion. It's in the center of whatever our conceptual space is. It means nothing. We need to create an embedding and store it with our event so that we can recall it. By default, we do not store embeddings with our events. The reason is because it costs money to generate them, and a little bit of time. It's really cheap compared to the completions with OpenAI. It's like 1/100th the cost. It's their cheapest model, so not horrible. In terms of adding cost and complexity, it's not the worst thing, but it does add a little bit of time. And you should be aware that you will need your OpenAI key in there, which I'll also need to paste in order to test this. Yeah, I mean, otherwise for these events, it's just database. You don't need any OpenAI for them. It's only when you use these embeddings, right? So let's create an embedding. I like all of this stuff, but I want to show you what an embedding looks like without all this. So I'm just going to kind of unwire it. I'm going to kind of get rid of that stuff here. I like all these nodes. We're going to want to use them in a second. But I'm just going to kind of disable them for a second. We'll leave them over there. And we can kind of bring this down here. So I've got my input, I've got my event destructure, and I've got my output. Kind of my standard stuff, right? I'm gonna, let's see. I have another new node that I really like called get values from object. And I can also do this and get rid of this destruction node. Maybe this is a little too off the beaten path right now, but I don't need this destruction node. Now I can just use this little node and delete this. But I'm wondering if maybe, since you guys are already using this, I'll show that next time. I'll show that in the next lesson, is better destructuring. Because this is such an ugly node. You know, all these, we only use this one. Anyway, so we've got our destructure node. It's taking our event input and breaking it out into all of these. And we want to take this content, which is the actual text I type in here. We want to take that content and we want to create an embedding of it and store it, right? Even before we store it, let's just see what the embedding is. So I'm going to go to my embeddings in my context menu, the embedding section, and I'm going to go to create text embedding, right? So, you know, we had all that complexity of what an embedding is, and like, well, embedding is really just like whatever comes out of here, you know. You don't really have to worry about what it is, actually. As long as it's the right type of data, and there is data, it's going to do something you want. So I wire up the execution chain with the triggers, and you can see now I have this embedding. This is an array of numbers, so I have to convert it to something that the output can see. So I'm going to go to the array view, array to JSON. This is just for, in this case, this is a really useful node, but for what we're doing right now, this is just so that we can visualize it as like as some text. Because we can't really print the array of numbers to the output. We have to make it something first, you know, some text. So basically what this says, it says, okay, make an array, make an embedding. For all our purposes, embeddings, vectors, and arrays are basically, they're represented the same. So we make an embedding. We're just going to convert that to JSON. JSON says, turn that into like something, some text that I can read, and then output that. We don't need this node usually for what we're doing. This is just to help us to visualize it. So that being said, well, this isn't going to work. And it's not going to work because I have to go get my OpenAI first. I have it in the cloud, but I don't have it in the dev. So I'm just going to log in really quick over here on the side. And I'm going to go get my API key. And I got to go paste it into here. And dev. Quick. Okay, got my key, pasted it in. Good to go. Let me just refresh really quick here. Good. Cool. Now, if I type in testing, bam, it went through. It took testing. It created a text embedding. And this is the embedding it came up with. It's some crazy thing that should probably be word wrapped. But let me just, can I open that somewhere? Can I log into HackMD? Wouldn't that be nice? No, guess not. Text editor. I don't know. I just want to like show you guys. Create a new text now. Great. This is the embedding it came back with, right? Crazy numbers. Just for the word testing. But it can only create it in one dimension. So it doesn't matter if I have an entire document or a single word, they're all going to get broken down to this single concept. So this is something to be very aware of, is you don't necessarily want your entire document to be one embedding, because it's probably not that accurate. You probably don't want a single word to be one embedding either necessarily, although it's probably fine. And so for this, you know, that's totally fine. Now, let's say I type in, this is a test. Well, the numbers are different, but they're actually pretty similar. You know, they're more or less very similar to each other. Probably not across every dimension, but certainly in a lot of these very, very similar. Because testing and this is a test are not a whole lot different. How about like I am a meat popsicle? Great movie. A little Fifth Element reference. And you can see these numbers are definitely more different. You know, 029 versus 012. Like, so this is clearly like conceptually very different than. And we could actually measure this as a number of like, how similar is it? And you could map that to be like, it's 90% similar, it's 10% similar, right? So we've created the text embedding, and now we've viewed it, but this is not helpful at all. We don't really, you know, I don't know what these numbers mean. I don't really care about these numbers. I need these to go magically behind the scenes somewhere. Okay, so we've created the text embedding, and now we've got a place to feed embeddings out into our event. Let's go up here. We're going to delete that array JSON. We don't need that anymore. We do need this conversation. We want the events to conversation, the echo. Now, when you're doing this, you might have a conversation node like this, and you might also have another conversation, right? I need my short term here, but I want my long term, right? Long term conversation. And maybe I only need one. I only need one event to come back from that long term, right? But for the intents and purposes of what we're doing here, we're just going to focus on this one node. We'll just say long term, and we'll make that one. So create the embedding. Great, from whatever came in. Now let's recall anything that is similar to the embedding we just created. The similarity search there is totally hidden from you. You don't have to worry about it. All you got to do is say, okay, when I am pulling some long-term conversation, you know, write that in, long-term conversation, or it's the long-term memory of combo. That's kind of nice. When I'm pulling that in, don't just get me the last 5. Get me the last 5 or 1 or whatever sorted by similarity of the input embedding. So whatever I type in here that comes in from the input, use that, make an embedding of it, and now go and compare it to all of the other embeddings you have and recall the most relevant one, right? Does that make sense? So this embedding input on the conversation recall node, event recall node, called the event recall, even though we renamed it a bit, is going to perform a similarity search for us. Oh, people are saying it's too small. Okay, let's zoom in a little bit. My bad. So once again, I have my input. I destructure it. I get the content out of the input, and I create an embedding of it, which gives me back the embedding right here. Now, once I've created the embedding, I'm using that as the input for this event recall. And instead of sorting by the most recent, it's now sorting by the most relevant, the most similar of the events whose content is the most similar to what I just wrote in. From there, we'll format it into a conversation, even though we don't necessarily need it to be. It'll at least say, like, you know, whatever user set it to whatever they said. We can echo that, and then we could output it. And let's save that. We'll store in a second. So I've already got some embeddings in here. I've already made some things. Hopefully, if I type in testorama, you can see that what it came back with was user testing assistant. Hello, is there anything specific with? Well, that user testing, remember, I typed in testing up here and it generated an embedding. And before this, I typed in testing and it saved the embedding as an event somewhere. So it's pulling back the testing event. It's only pulling back the testing event here. It seems to be formatting it so it's pulling back the testing event and the response event. I think that's how it's supposed to be. Because you would actually, in this case of a conversation, you'd want what I said as well as what the person responding, you know, back said. And in this case, I probably stored the embedding for both of these to be the input. We can talk about that in a second, because we're going to have to store events now. But more or less, I already had some events. It went in and it worked. It recalled the event of testing, which is very similar to what I wrote, which is testorama. Cool. It converted that conversation, it echoed it, and it outputted it. Now we need to store the event. Now, I'll just set it up the way we've been setting it up, which is it will echo out whatever you echoed in. That'll be the content. And the event input is going to be from over there. And now you can see, well, we have this embedding input. So on the store event node, if you store it without an embedding, it stores a 0 empty embedding. If you store it with an embedding, it will save it with that embedding to be recalled later. Now, what happens if I use this embedding? Well, it's going to associate both the input event and the response, the recall. It's going to search for this input, and it's going to store whatever events with that input. So let's make that a little less abstract. We're going to say this is speaker input, and that's the conversation type. And we'll clone that. And this is going to be called the agent input, or agent response, right? Cool. So I store the embedding on the speaker input, and that's right. I could store the same embedding on the response, and what's going to happen is that it's not going to search by the response text. It's going to search by the embedding of the original input text. This could be a bug, or it could be a feature. Let's say you're trying to search for the appropriate response. If there's already a response cached that's similar, like, you've got people talking to you all the time, and you want to just give them the pre-canned response for whatever, if they said something. I already answered that to Bob yesterday. Well, you could search by the embeddings. You could actually store the response by the question, like the answer, by the question that was asked. And so instead of searching through the answers, you're actually searching through the question. And if you have a similar question that somebody already asked, you could pull in the response to that question using the question embedding, not the answer embedding. So in this case, both the conversation that I had with what the user said to the agent and what the agent said back both share the same embedding, right? But there might be a case where you actually don't want that. Let's say I ask the agent, what color are your eyes? And the agent says, my eyes are blue. Then the next day, I could, if I say, what color are your eyes? Well, it will go and search, and chances are, because they both say eyes, it might, with good certainty, come up with, well, you said my eyes are, I said my eyes are blue. But what if I wanted to search by, describe all of the colors of your facial features, or something? Then, in that case, it doesn't know that I'm talking about its eyes. It knows it's talking about color, but it's a very fuzzy thing. So maybe in that case, I actually want the agent's response to be the thing that's recorded, not the question that's recorded. Sorry, I'm kind of pulling this abstractly out of my ass as an example, but it's a key point here that in this, all the conversation is stored by this one embedding. It doesn't have to be that way. I can clone this embedding, or this node, and I can have it here. And I could say, okay, well, let's have an embedding for the input that's actually different from the embedding of what the response agent says. Now, obviously, we have an echo node here, but imagine this is a text generator. It's generating some text. Maybe we'll just make a text generator. Might just be more valuable here. Generate text, and let's use GPT 3.5 Turbo. And we will plug that in to the input. Oh, weird bug. Gotta save and refresh the window. Just adding a text generator in there so that we're not just putting embeddings for the same things on both sides. That would be weird. It's a lot easier to illustrate actual example. So this is actually very similar to what your agent looks like. This is basically a complete agent now. Has a system directive, which we'll give it text variable. We'll do elephant today. Respond to the user as elephant. Cool. Done pirates and towels and various things. Today's an elephant. And that's the system directive to this text generator. And that's kind of all we need. It's going to generate some text, hopefully. Cool. So let's recap. Input comes in, we destructure it, we get the content, We create an embedding of the content. We go and recall all events similar to that embedding. We convert that recollection into conversation. If we, we don't have to. We can do different things, but one of the things we can do is we can take that conversation and, well, we're using it as input right now into our generator. It's a little jank. We probably want use a conversation node and blah, 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 but don't worry about it. We're generating. We're creating an output from that, the response is coming from that generator. We're storing the original input in this speaker input node, right? That's what the person said, which we should make sure we're capturing the content there. And then we're recording the output of the response from the agent in this agent response store event node, which we should fill out. But they have the same embedding right now, right? Both the input and the response are both stored with the same embedding. That's fine, but we should probably generate a second embedding for the response. And so after the speaker input, we will create a new embedding. The embedding is going to take the output of the generate text as the input. And then that embedding node will feed into the embedding of our response. So now we're creating two embeddings. Create an embedding for the input, which lets us do similarity matching. And we'll store that embedding later when we store that event. And then we create a second embedding for the second event. Now, we could create one embedding for both. We just did that. But, and for if you're cost conscious, maybe that's what you want to do. But this is how we can create now two embeddings, each of which can be searched independently and will be recalled. So fresh, and I type in testing, going through everything. It's going to take a second. It generated, it output, it's stored, it generated another embedding, and it's stored. Testing. I apologize. I am an elephant language model and cannot perform your awesome. So if I go and I look in here, I believe that we are in reverse ascending order. So it's, you can see, I apologize. Can't see the text there, but it's, I'm an elephant language model and I can perform actions, right? And that has, well, we're not showing the embedding on here because it's a crazy number, but this has an associated as an event, as do all of these. So now when I go back and I type in elephant, well, I'm actually not going to see, let's see, how could I get it to show me, what do I want to see? I want to see the memory as the output. I don't want to, I actually just want to see the last one. Are people having trouble hearing me? I know Dave is. I could see if there's something I can do on the Discord to try to fix it. Unfortunately, we're about 90% of the way through, so be a little bit late. Echo cancellation, automatic gain control. I don't know. I could mess with these a little bit. I'm going to turn off noise suppression. How about that? Maybe that's a little better. Cool. Okay. So we've gone through and done all this. Let's just see what happens if I type in generates, and it gives me back. It's a little complicated, but you'll notice that it says, I apologize, I'm an elephant language model. And so when it came back with the response, which I just grabbed the recall event. I'm not outputting what the response of the agent was. I'm just showing you what the event is here. I've hardwired that in. You can see that it's giving me back what its last conversation about elephants was. The most similar thing to I apologize, an elephant language model of the available events was me writing elephant. That's the one it responded with. So now we've effectively created sort of a long-term memory loop where it goes in and it grabs whatever conversation is relevant or similar to what it's searching for, and it injects that. Great. We have long-term memory now. This is how we model it. But what happened to our short-term memory? We still need that too. How do we put these things together? So how we put them together, well, there's a little bit of formatting to make this generate text node work cleaner, and I'm going to kind of work on this on my own and present a nice template of this today that I'll post, so you guys can just have the entire end of this ready to go with no headaches or hangups. But I'll show you how we can at least build it out here, and then I foresee there'll be a little bit of kludge that we kind of want to mess with, which is how we're inputting the long-term events into our text generator. Haven't really done it with the ChatGPT model yet. We might have to do combine some things in a template node first before they go in here. Don't worry about that. What we're going to talk about right now is just doing the short-term memory, long-term memory, and then we'll provide you with a spell that covers all of this if you're just kind of want to upgrade it. But also if you want to implement this in your existing spells, great. That's awesome. That's a great way to learn. So we have short-term memory. Now, long-term memory. Let's add short-term memory. Well, we'll add an event for event recall, just as we did. Now, we can parallelize some of this stuff. Well, we'll parallel next. That's going to be a really, really good one. If you guys remind me, we'll do a wait for all and for loop stuff. We'll do this. Basically, parallel means we can actually be recalling the short-term memory and the long at the same time. That way, we're not making our graph slower and slower and slower as we add processes into it. You'll notice this purple kind of execution goes from here to here to here to here. So we need to insert our other event recall in here, and it's going to add a little bit of latency. So in the next one, I'll show you how to make that run faster in the next Academy session. But in the meantime, we're going to still continue to chain these things one after another. So create the text embedding. We will route the execution trigger into our first event recall, which we'll call short-term convo. And we'll make that the conversation type. We will not be passing an embedding into this one, right? This is our short-term. And then we will be passing that into our long-term convo here, which we are passing the embedding into. And then this is where things get a little funky because we actually want this events to conversation node here to feed our short term, but we're just going to make two. So we have, clone that. We have an events to conversation for our long-term memory. And we have an events to conversation for our short-term. And our events to conversation for our long-term memory is going to feed the input. We actually don't need this. We don't need the events conversation because the chat has a conversation. We're just going to take the short-term memory here, and we're going to take the events, and we're going to put that into the conversation input of our generate text node. So basically, what we did before, which is get the short-term memory, shove it into the conversation node. Now, let's clean this up a little bit. I kind of don't like our wires, but obviously it's nice for showing the flow, but sometimes we'll be adding some stuff so like if you click on something, you'll be able to highlight the wire stuff. And then we just need to make sure our trigger is here, text variables there, output. I don't know if you guys have ever seen like the Unreal blueprints from hell kind of stuff. It can get pretty crazy. But this kind of describes the flow. Oops. As you can see, short-term convo call, long-term convo takes the embedding. This is going to feed into our input for now, and our short-term convo is feeding into our conversation. What we really need to do is create a system directive that combines our long-term memory and our elephant description, and then we can feed that into here. Maybe we'll do that next. But even outside of that, this will work, right? This will give us some sort of input response. Hello there. does the deal. You can see it's still printing out the memory because we actually don't have it printing the response. But that's cool. It's doing its thing. We just need to make sure that this is getting the result of the generation for the output. Well, hey, what's up? Hello. Is there anything I can assist you in with regarding testing? Because I've been talking to it about testing, so now it's got all this conversation built up of testing. That's all it seems to want. No, done testing. How was your day? It's got to be nice to the language model. Show a little empathy. As an elephant language model, I am not able to assist with technical issues. I get that. Okay, so why is that happening? Well, because we can't just feed our long-term memory directly into our input. We need to combine our long with what we just said, right? That's kind of the last missing piece here. Okay, well then how do we do that? We're going to add a text template node. I think we might have showed this off before. Maybe not. Maybe we haven't gotten into this. We can combine different pieces of text object into a more complex prompt using the text template node. What we're going to add here is a directive for our system directive, and we're going to add a long term. And these are going to be inputs on here, directive and long term. And instead of feeding this text variable and this events conversation into our generate text, we'll feed this text variable into our directive and this events conversation into our long term. And then the input will actually be the input of our user. Right? So this is like ChatGPT, right? We need to prime it with some context in the system directive. We are providing the previous conversation we had, which is our short-term memory. And then we're also adding the input, which is the new input that we want the agent to respond to. We'll probably have to lengthen this out a little bit. Just, generate text should come after the text template. So we will trigger the text template, and then we'll take the output of the text template as our system directive. Now we got one last thing. We'll probably cover the text template in more detail in the next lecture. It's a really important one. But we use a very standard format for creating this template. As you can see on the side, we have long-term and directive. These are our inputs. This is where string information is coming in. And we can combine those into a single prompt using what's called handlebars notation. So handlebars notation, there's a thing called handlebars.js that we use. You can look at all the tutorials on this here at handlebarsjs.com. All it really means is double bracket something and stick it in there. So this is the basic usage, is this kind of double bracket thing, blah, blah, blah. Cool. The way we use it in this case would be long term and then directive. Those will be on different lines from each other. Save that. And now we've combined our you're an elephant with our long-term memory, right? Now the memory comes in here and sticks out there, then the directive goes there, then the conversation will get injected under that, and then finally our. So now we should have something coherent. Tell me about your day. As an artificial intelligence language model, I don't have the ability to experience a day like humans or elephants do. However, I'm always here to help. Okay, so you won't tell me about, you don't have days. But, it was coherent. It answered my question, at least it understood what I was talking about. So now look, we've got all the things. We've got long-term memory and recall, short-term memory, our nice response. We're storing it all. This is the finally, if you wanted, your agent that remembers you, what you said 5 days ago, this is the core loop. This is how we get there, right? Everything else beyond this is going to be going out and finding information or maybe adding cool skills or whatever. But this is the core loop. So answering questions. How is the long-term indirective being parsed so it doesn't just think you've appended it, the long-term string to the directive text? No, that's exactly what I've done. I have appended the long-term. They are separated by this new line. I could do like this, and then they would just be like one thing. There's no space. There's smash. I could do something like this. Give them a little bit of new line space. The system directive can actually be quite long, and chances are that we're not using it as much as we could. The other thing is the system directive is designed to solve that problem we were having in the sandbox. You know, I don't think I probably closed it. You know how I have like if I've got a bunch of text down here, that's all good. The stuff at the top gets kind of lost in my context. The system directive is designed to make sure that whatever your instruction still stays relevant even through the conversation. This is a new thing in ChatGPT that the previous transformer models didn't do, is that anything at the top gets lost and you lose your personality. The system directive is an attempt to pull that context back out and weight it heavier toward the end so that, I mean, think about OpenAI, right? People were doing all these jailbreaks by overloading the context and then giving it a new personality, and it had completely forgotten the old one. And so the system directive was like, well, that's going to happen, so let's try and take this one thing and weight it more so that you can't jailbreak it. It's always going to value this thing over the whatever their prompt injection attack is. And this is very useful for us because it means we can just do that, and our long-term memories will actually be weighted fairly heavily with our system directive, even if we have a long chat. So, sorry, it's a mouthful. Hope that kind of explains. Your system directive can be quite long, and it could be all of the context that you stuck in. Like if you were working with older language models pre-chat, this is kind of where you put all your context. So, I think that I've covered everything. This is another long one. Well, I stayed under 90 minutes, which is kind of impressive. But you know, single topic, very big topic. We'll try and I'll talk to the team, and we'll also pass around all the lecture notes and different resources that are helpful. If you guys have any questions about this particular lecture, I know this is really one of the hardest concepts for us to grasp. Beyond this point, we're going to be looking at things like Google search, maybe the loop agent, so you can have ongoing tasks. Maybe some of the other connectors. We just added Blue Sky. We're about to add an email connector, so you could have like an email assistant. So yeah, we'll figure out what we cover next. But I think mostly it's going to be more in here in the graph, building stuff, learning about some of the new nodes, learning some flow and stuff. And we're probably mostly out of the weeds on like the more conceptual, like sitting there explaining the background stuff. Cool. Any questions or anything before we kind of wrap this here? And if you have any requests too for things you would like to learn, that helps us a lot to kind of dictate where the direction of this goes. Oh yeah, I'm also working on a calendar integration that was requested by one of our alpha users. So things like that. It gives us a bit of direction. It tells us what we should be focusing on, and we want this to be fun. And like, wow, cool. Next week I'm going to learn this new thing. So yeah, so your requests help us a lot. I'll wait one more minute for questions. But it looks like everybody's wrapping up. So thank you guys so much for this.